everyone. In previous tutorials, we have introduced the unsigned binary representation. And in this tutorial, we're going to introduce a new binary representation that will allow us to represent negative numbers. And that new binary representation is called the 2's complement binary representation, or the 2's complement binary notation. In this tutorial, we are going to cover four elements, and it will be a two-part tutorial. So in the first part, I'm going to cover the first two elements, how does it work, and range. And in the second part of this tutorial, I am going to talk about overflow and something that I called length of determination. So let's start. So just like in the unsigned binary notation, we have bits or places or positions, and each of these places have a value, right? Like this first bit has a value of 1, this has a value of 2 to the power of 1, this has a value of 2 to the power of 2, and this has a value of 2 to the power of 3, raised to the power of 3. So in the 2's complement binary notation, it's exactly the same, except that last bit right here, it has a negative value. It has a negative value, right? Let's drag this a little bit here. Yeah, it has a negative value. So to figure out the value of any number in the 2's complement binary notation, all we need to do is add up all the ones, just like the unsigned binary notation, except that keep in mind that this is called the most, this one here is called the most significant bit. No, it keeps doing this. This is called, that last bit right there is called the most significant bits. Most significant bit. So keep in mind, if you have a number that ends with 1 in the most significant bit in the 2's complement binary notation, that means it's a negative number. If it ends with 0, that means it is a positive number, as we will see in the example. So let's, for example, take this number. If we are using the unsigned binary notation, which only represent positive numbers, this number would be 11. Why? Because this is 8, and this is 1, and this is 2, and this is 4. So if you add up all the ones, that would be 1 plus 2, that would be 10, plus 1, that would be 11. In the 2's complement binary notation, since we said if the most significant bit has 1, that means the whole number is negative. If it has 0, that means the whole number is positive. So let's add, so this weight here, this is going to be minus, this is going to be minus 8. So let's add up in the 2's complement binary notation, this is minus 8. So let's add up all the ones. So 1 plus 2 plus minus 8. Okay, so that is minus 5. So this number right here, in 2's complement binary notation, it's minus 5. How do you write positive 5? Well, again, here are the weights, right? Bearing in mind that this last one is minus. So I put 1 here, 0, and 1, and 0. So this is how you write plus 5 in 2's complement binary notation. You will notice that it's exactly like the unsigned binary notation, except that you need to put this 0 in the most significant bit to indicate that this is indeed a positive number, because if you just did this, it will end up being a negative number, which will be minus 4 or minus 4 plus 1. So this one here is equal to minus 3. Okay, you need to put 0 here to make it plus 5. So you add the numbers instead of subtracting. Okay, so now that we know how to figure out the value of any number in the 2's complement binary notation, how do I actually arrive at these values? Meaning, if someone asked me, can you write down -5 in 2's complement binary notation? How do I arrive at this value? Well, it's very simple. So I'm going to start anew. What you do is you follow a 2-steps algorithm first, and that is to arrive at a negative value in the 2's complement binary notation. First, you need to write the positive equivalent, or the positive number of that value. Okay, first thing, write the positive equivalent. Second, copy the bits from right to left till 1 is copied, and then complement or complement or reverse the remaining bits. Okay. So this might sound a little bit confusing, but once I give you an example, it will make a lot of sense. So let's take an example. Let's say, okay, how do I write -5 in 2's complement binary notation? So first, let's follow the algorithm. Write the positive equivalent, right? Write the positive equivalent of that number. Okay. So the positive equivalent of that number would be, if this is 1, 2, 4, 8, would be 1, 0, 1. And remember to put 1 here, right? So this is +5. That's the first step. And that's how you write +5 normally in the 2's complement binary notation. Copy the bits. The second part of the algorithm is to copy the bits from right to left till 1 is copied, and then reverse the orders. So we're going to start from right to left, and we copy the bits exactly till 1 is copied. Fortunately, the first bit here is 1, so we copy this bit down here. And then we are going to reverse the order of the remaining bits, or complement the order of the the remaining bits. So to reverse, 0 becomes 1, 1 becomes 0, and 0 becomes 1. Voila, there you go. So this is -5 in 2's complement. And to excuse me, and to verify that, all we need to do is we add them up. We said this is if this has 1, it will be minus, it will be negative. So -8 plus +3, that would be -5. And by the way, if you reverse this process again, you will arrive at the positive number, right? So if you copy bits from right to left, that would be 1, and then reverse the order. 1 becomes 0, 0 becomes 1, 1 becomes 0. You arrive at +5 again. So that means that you actually can use this process to convert, to know the value of any negative number in the 2's complement. Let's take another example. If you have this 1, 2, 4, 8. If you have this value right here, can you figure out what number is this in 2's complement? Well, it's -8 plus 1, so that should be -7, right? What if I want to know the value by converting it back to its positive equivalent? No problem. So here's what I'm going to do. I'm going to copy values from right to left, 1, and then reverse. So 0 becomes 1, 0 becomes 1, and then this 1 becomes 0. So this is +7. 1 plus 2 plus 4, that is +7. So that's how I know that this is minus 7, either by subtracting the weight, the negative weight, by adding the negative weights of the most significant bit to all the other weights, but in a negative sign, or converting it to its positive equivalent, and when I get the absolute value, I just add a negative sign. Okay. So now that this is covered, I think we've covered the first part of how does 2's complement binary notation work. We're going to start talking about range. So as a rule of thumb, an in-bit, we can generally say that an in-bit's 2's complement an in-bits 2's complement binary system is capable of representing numbers ranging from minus 2 to the power of n minus 1 to plus 2 to the power of n minus 1 minus 1. So it actually all depends on the number of bits in that 2's complement binary notation. In the previous example, if we have a 4 bits 2's complement binary system, it will represent less numbers than if we have, let's say, 8 bits 2's complement binary system, right? And here's the equation that we use to arrive at the range. So let's take this example where n here represents the number of digits or positions. So if we have a 4 digits, or if you have a 4 positions, 4 bits, if we have a 4 bits 2's complement binary system, it's capable of representing numbers ranging from 2 to the power of n, which is 4 at this point, n minus 1, so that would be 3, to 2 to the power of n minus 1, which is, at this case it's 3 minus 1 again. So that would be minus 8, that would be minus 8 to plus 7. So in a 4 bits 2's complement binary system, it is capable of representing numbers ranging from minus 7 to plus minus 8 to plus 7. And this is going to take us to the last part, and this is actually the last part in this tutorial. Thank you guys for watching, and I'm going to see you on the second part where we talk about overflow and length determination. Thank you so much.